So is my screen visible to everyone? Am I audible? Please respond to this. How do I know that you guys are here? Okay. Is my screen visible to all of you? Okay. Thank you so much. Okay, so good evening all of you. Today it is requested to all of you please join on time. Okay, fine. So good evening to all of you. Today we are going to discuss about the Introductory Organic Chemistry first course. It is a part 1. So it is an NPTEL platform course which is running on the NPTEL platform, and the course instructors are Professor Harinath Chakrapani and Professor Neeraja Dashaputre. They are from ISER Pune. So I am your PMR teaching assistant Simran. So this course is basically of 8 weeks, and it will be running for 8 weeks. So I will be taking your tutorials every week on Saturday 6 to 8. So I hope to see you all. And today we are going to discuss about very basic questions of chemistry, guys. So I'm starting with very basic concepts. So we will be clarifying those concepts and then we will move towards. So the week one syllabus is the structure of atom and molecules, and here also you will get to know about the molecular orbital theory and the hybridization, resonating structures, how you are going to assign that. So these are the topics which we are covering in this lecture. So am I audible, right? Okay, thank you. So starting with problem one, here here is given value is the structure of dibromocarbene. So here the dibromocarbene, the question is saying that has a lone pair of electron and two separate covalent bonds, that is from it is forming with bromine atoms, right? So they are asking the formal charge on the carbon atom of this dibromocarbene. So you have to calculate the formal charge on the dibromocarbene. So as you can see, this carbon is connected to two bromine atom, and for calculating the formal charge, you have a particular formula, right? So I'm going through a very basic knowledge. So I hope that all of you are considering my concern, that I need to know that how much you have, right? How much knowledge you have, and I am building up on that, right? So we are starting with very basic questions. So here you have to calculate only the formal charge on an atom. So what is meant by the formal charge? Now it is there is a formula to calculate the formal charge of an atom. So here we can see that here the VE denotes the valence electron for the neutral atom. The NBE corresponds to the non-bonding valence electron. That is the lone pair of atom which is being present on an atom. And B is the number of bonds that an atom is now forming, right? So based on these three things, we have to calculate the formal charge. So now just tell me, what is the valency of carbon? Anyone knows? How many bonds can carbon? Yeah, four. Yeah, very good. Valency of carbon is 4, right? So first thing is sorted. The valence electron neutral atom has is 4, right? Now the non-bonded electron, that is the lone pair of electron that are present on this dibromocarbene species. How many number of lone pair electrons are present? Right. So the lone pair is 1, but the lone pair electrons are 2, right? So this is also sorted. Now we have the question of number of bonds that is formed. So now how many number of bonds are there currently which is forming by the carbon? Right, 2. So here we can see that the formal charge, we can calculate that first 4 is the valency of the atom, carbon atom, right? And then you have answered that 2 is the number of lone pair of electron that are present, and also another thing is also 2, that is what? The number of bond that is formed by the carbon here. Okay, so what is the total number? Comes out to be, yeah, 0. So what will be the formal charge now on the dibromocarbene? That would be 0. So the correct answer will be this. Fine. Any doubt in this question, guys? Is it clear to all of you, or any of you has any doubt? Please feel free to like question. Any doubts? Okay, so I'm hoping that all of you understand this concept. Yeah, yeah. The two electrons that are present on the carbon. Where are the two electrons? I'm not actually getting your question. Yeah, yeah. That lone pair, we are contributing that lone pair, right? Here in the formal charge formula, what you can see is we are calculating the valence electron of an atom. In the case of carbon, that is 4, right? Now the contribution of non-bonding valence electron comes. The non-bonding electrons is coming from the lone pair only. So now in this case, we have one lone pair, right? So if one lone pair is there, the contribution is 2, because the number of electrons are 2, right? If in the place of this lone pair, if you have a radical, right? If you have a radical on this carbon, then the contribution for the electron will be 1. For radical, we are counting one electron, but for lone pair, we are counting two electrons. So that is why we are writing here 2. 4, that is the valency of the carbon, 2, that is the non-bonded electrons, and again 2 because of the number of bonds that are is currently forming by the carbon, right? So this is how you are going to calculate the formal charge of the carbon. Is it clear now? Yeah. Okay. I think someone wants to join. Okay. Fine. It's a request to all of you, please join on time. Okay. So coming to the question number 2. Here they are asking the total number of lone pair of electrons that are present on I3 minus ion. Here this I3 is corresponding, I'm allowing you today only because it is the first session, but guys please be on time from next time onwards. So where was I? So here they are asking the total number of lone pair of electrons in I3 minus ion. So here I3 is corresponding. Everyone, please switch off your mics, please. Yeah, thank you. So the total number of lone pair of electrons in I3 minus ion. So here I3 is corresponding to this I3, not this, guys. Sorry for the typo. This is this molecule, right? So now you have to calculate the lone pair of electron that are present on this species. So how you are going to calculate that? See, first of all, you need to know what is the valence electron that are present on iodine, single iodine I am talking about. So the valence electrons that are present on iodine, can anyone tell me quickly how many? Yeah, very good. The 7 is the valence electron that are found on the single iodine atom, right? So here we are contributing for the 3 iodine atoms. So now the valence number of electrons that would be present will be 7 into 3, that is 21. And where is this 1 coming from? This is a negative charge, right? So 1 electron is adding up. That is why we are adding 1 plus 1, right? So the total number of valence electrons now would be 22, right? So now they are asking that how many number of lone pair of electrons will be there. Now you will be calculating this according to the bonding. So here iodine are connected to two other iodine atoms via single bond, right? So now you can say that these are the number of electrons. So 1, 2, 3, 4, 5, 6. 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. And this is also an electron, right? Because of which they are forming the co- covalent bond, right? So how many electrons are in total? There are 22 electrons in total. So how many lone pair will be there? See, there is only two sigma bonds that are present, and all of the electrons are free, right? So here one lone pair of electron is there. Here is another. This is also a lone pair of electron, right? This is also a lone pair of electron. This is also, this is also, and this. So these are the lone pair of electron that are present on I3 minus ion. Because I3, the three iodine atoms are connecting towards each other by only sigma bond. Two sigma bonds are present in between them. So how many number of lone pair of electrons are there? Can anyone tell me quickly? Yeah, very good. So there are nine uh, lone pair of electron that are present on I3 minus ion, right? So the correct option will be option C. Okay. Any questions? Any questions on this part, guys? Okay. No questions. Shall I move forward? Guys, please put your mics off. Thank you. Okay, so if there is no question, we are moving to forward. So, question number three. So this is a very basic question. I hope everyone can answer this very quickly. So they are asking BCl3 is a planar molecule, whereas NCl3 is a pyramidal molecule. Because the first option is BCl bond is more polar than NaCl bond. Second option is NCl bond is more covalent than BCl bond. Third is the nitrogen atom is smaller than boron atom. And the D option is BCl3 has no lone pair of electron, but NCl3 has a lone pair of electrons. So, any guesses? Very good. Option D is the right answer. Why? See, what is happening here is BCl3, as you can see, doesn't have the lone pair of electrons. Boron is not having any lone pair of electron with him because all the bonds are occupied. But here, in the nitrogen case, one lone pair of electrons are present. So here, the shape becomes the pyramidal because of the lone pair bond pair repulsion, right? But here in the BCl3 case, there is no lone pair that is present. That is why we are getting a planar molecule for BCl3, but not a planar molecule for NCl3. It is getting pyramidal because of the lone pair bond pair repulsion, right? So the correct option is D. So any questions in this particular question? Any doubts? Guys, I'm saying that only girls are responding to me. Why boys are not responding to me? Are they sleeping? Okay, girls, please respond. Any doubts? Okay, okay. So I'm moving forward. So coming to the problem number four. Here, they are asking the number of resonance structure in ozone are. So you have to calculate the number of resonance structure that can be possible in a ozone molecule. So now, first of all, you have to know what is a ozone molecule. So ozone molecule is nothing but an O that is connected to this two oxygen molecule in this fashion. So they are asking how many resonance structure can be possible. So here you can see that you can have a double bond although here as well and here as well. So these are the two forms that I am writing. Instead of this corrected one, here we are seeing it like this. Okay, this is oxygen, again this is oxygen, this is what ozone is. Okay, but it is not neutral species, right? So here what happens here is a charge transfer takes place, and this kind of resonance structure is going to form. So oxygen, this will go here, sorry, this will go here, and this positive charge will come on this oxygen, and this negative charge is coming on this oxygen, and this double bond is converting into a single bond, right? So this is what happening here. And also you can write the similar structure with this. Here this double bond is getting on this, and this positive charge is getting on this oxygen atom, and here a negative charge is getting formed, right? So this is the second resonating structure which you can think of. Any other resonating structure you guys can think of other than these two? Anyone? Okay. So these are the two structures that can be feasible. These are the two resonating structure which is feasible for this ozone molecule. So how many resonance structure can be possible for ozone? Can anyone answer now? Two. Very good. So there are only two structures that are possible for ozone, because here one double bond can get onto this oxygen, the bonded electron can get onto this oxygen and getting a negative charge, and this oxygen will get a positive charge. The second scenario which can happen with this oxygen as well. So that is why there is only two resonance structure that can be possible for ozone molecule, right? So any doubts in this question, guys? Okay, so there are no doubts, right? So I'm moving forward. So here is the problem number 5. Which bond is most polar? Is it the CLF bond, BRF bond, IF, FF, or none of the above? So, which bond is most polar bond? So, polarity actually depends on the electronegativity. So, how many electronegative atom is defines the polarity of that bond, basically. So, any guesses here? Which will be the answer? IF. Very good. Any other opinion? Okay, IF. So guys, here what you need to know. So those of you who didn't understand why IF is the most polar bond, see, here the concept comes into play, that is the electronegativity. So as we are moving towards the halogen atom down the group, fluorine, chlorine, bromine, iodine, the electronegativity trend is getting decreased, right? So fluorine is much more electronegative than chlorine, which in turn is more electronegative than bromine, and which in turn is much more electronegative than iodine, right? So here this particular trend get followed. So now the question is asking the most polar bond will be. So here if we think about the Cl and F bond, although we know that fluorine is more electronegative than chlorine, but the electronegativity difference between chlorine and fluorine is not that much high, right? Fluorine is just way more electronegative than chlorine, right? So it is not as much higher than chlorine. Here you can see the electronegativity numbers. So fluorine is 4, but chlorine is 3. So the bond is not very much polar because of the less electronegativity difference. But when you come to the second option, that is bromine, so in the case of bromine, the electronegativity difference between bromine and fluorine is higher than fluorine and chlorine. So it is more polar than fluorine chlorine bond, but it is not yet polar than iodine and fluorine bond, because there is way more electronegativity difference when we come to fluorine and iodine. So iodine and fluorine having the very high electronegativity difference, that is why the fluorine and iodine bond is more polar than fluorine chlorine and fluorine bromine bond. And fluorine fluorine is the least, right? Because there is no electronegativity difference at all. This is also 4 and this is also 4, right? The second thing. So here the correct answer will be the iodine and fluorine bond, because iodine and fluorine has a higher difference in the electronegativity value than any other, and polarity depends on the electronegativity itself. So fluorine is way more electronegative than iodine. That is why it is like attracting the shared pair of electron towards itself very high than iodine. So the bond distance between I and F is high because of the stretching of the electron towards the fluorine. So that is why I and F having the higher bond length, and the polarity of this bond will get increased. So this is why IF bond is the most polar in all the given options. So, any doubt in this? I hope you guys got the answer. Any doubts? Any doubts, guys? Okay. So, I hope all of you have got the answer. If not, please ask. Okay. So, I'm going to the problem number 6 now. So it is a very straightforward problem. So here you only have to know the structure of the P4O10 and nothing else. Okay. So here they are asking that each phosphorus of P4O10 molecule is attached to how many number of oxygen atoms? So anyone knows the structure of P4O10? Anyone? Can anyone answer how many oxygen atoms will be attached to phosphorus in this P4O10 or P2O5? Okay, guys. So you need to know the real structure of P4O10 here. So this is the complex structure of this P4O10. So it is very fascinating, right? So here we have to calculate that how many oxygen atoms are connected to this phosphorus. So as I have shown you the structure, you can clearly say that yes, the four oxygen atoms, that is 1, 2, 3, and 4. There are four oxygen atoms that are directly connected to this phosphorus. So how now tell me how many oxygen atoms are connected to P4O10 phosphorus? 4. Okay, so this question is very straightforward, although you have to know the structure of P4O10. So it is a very basic question, guys, and you have to know the P4O10, P2O5 kind of structures, because it is very important, right? So whenever you are answering these kind of questions, you are just have to know the structure, you have to visualize it and get the answer, right? So coming to the problem number 7. I hope problem number 6 is clear to all of you. It is a very straightforward question, right? Yeah. Sorry, I didn't get your question. What is the question? Okay, other than structure, any other way to find out the. Actually, we are the organic, actually, me as an organic people. So, I will suggest you to learn the structure only. Focus on the structure only, because, see, you know the valency of the phosphorus, how many bonds it can make, right? And you have to arrange these four phosphorus according to the oxygen atom connectivity. If you don't know the structure, you know that phosphorus has this much of valency and it will coordinate to that one only, right? So phosphorus having this valency will coordinate to four bonds or make five bonds, sorry. So how you are going to suggest that? So here oxygen having a one double bond, but although all three bonds are single, so now we can say that four oxygen atoms are there, but I will say that probably go for the structure only rather than the tricks. So that would be better. Okay. Okay. So coming to the problem 7, here it is a bit not tricky but trivial question it is, but still, see, they are asking when O2 changes to O2 minus, the electron goes to which of the orbitals? So, for knowing that O2 has how many electrons and how many orbitals are there, you first have to know about the oxygen, and then only you can say that oxygen with another electron, that is a extra electron, that this electron will occupy which of the orbital of this oxygen, you can say, right? So first you have to know the electronic configuration of oxygen. So oxygen has how many valence electron in their shell? Huh. So there are six electrons in the valence shell, right? Okay. So O2 will be having, is it six? Yeah, 12. So, so guys, in total, it is 12, the valence electron, but the electron that oxygen possess is 16, right? I'm not calculating the valence. I'm also calculating the whole number of electron that it would be having. Okay, so oxygen molecule in total will be having yes, 16 electrons, right? So now you have to know about the molecular orbital diagram. So you have to arrange those electrons into these shells. Sigma 1s, sigma 2s, sigma 2p, you have to arrange in that, right? So here we are incorporating that 16 electrons in these shells. So here, as you know, one molecular orbital will generate two atomic orbital, that is one anti-bonding and one bonding orbitals, right? This is the basic concept behind it. So higher energy orbital is the anti-bonding orbital, and the lower energy orbital is the bonding orbital. So here you have to arrange these 16 electrons in these orbitals. So how you are going to arrange is, here this 1s is there, but I am not showing here. This 1s is having how many electrons? Sigma 1s and sigma 1s star. Star corresponds to what? Anti-bonding, right? So these are the electrons that are present already. So 18 electrons are uh, there, 16 electrons are there. So here you have to calculate that here two electrons are there, and again here in the anti-bonding two electrons are there. This is the anti-bonding orbital for this 1s. Okay. So 2 to 4. 4 electrons are sorted. Now you have 2s orbital with higher energy of 1s. So here also you can have 4 electrons, sigma 1, sigma 2s and sigma 2s star. Fine. So you have to first write the electronic configuration of oxygen according to sigma 1s, sigma 1s star, sigma 2s, sigma 2s star, sigma 2p. Right? So guys, as we have 16 electrons to arrange, here we have 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and 15 and 16. As you know that according to Hund's rule, you can place the electrons singly and then you have to occupy that. Okay. So here we are placing this electron singly in this pi star orbital. So here you have to know the electronic configuration first, and you have to arrange those electrons into the respective orbitals. Okay. So now here they are asking, this is all about the oxygen molecule. This is about O2. This is O2. Fine. So now they are asking this, when O2 is changing to O2 minus. What is meant by O2 minus? One extra electron is coming, right? One extra electron is coming. So now tell me, which is the orbital in which the electron will add up now? Yeah, pi star. Because here pi star is singly occupied, right? It doesn't have two electrons. It is not fully occupied. This is partially occupied. So now any electron which is adding will come into this pi star orbital, and then after filling this pi star, the sigma star will fill, right? So here they are asking, when oxygen is changes to O2 minus, the electron is coming to which of the orbital? So is it pi orbital? Is it sigma? Is it pi star or the sigma star orbital? So which will be the orbital? That is pi star orbital. So electron is adding to pi star orbital. So this is the molecular orbital diagram, and how this is how you can actually write the configuration using the MOT theory, and also you can assign that the electron will add to which of the orbitals and how these orbitals are segregated. So this is what MOT will tells us, right? So any question in this? Any doubts? Okay. So I'll consider that everyone knows MOT. Okay. So you guys are good with writing these electronic configuration, I think. So this is good for me. So here, if anyone has doubt, please ask, guys. Those who don't know, I'm here for those only. Please, please, please ask me questions so that I can clarify that. Okay. Yep. Hmm. 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 See, it is not about forming and not forming the bond. See here, pi star orbital is also playing the role, because see, if how can I tell you? See, here also the sigma s of 1 and sigma s of 2. What I am trying to show you is this: anti-bonding orbitals are generated from the molecular orbital only, right? It is not about they are forming the bond, they are not forming the bond, they are actually here, right? So electrons are actually filling in these orbitals. It is the higher energy orbitals, but it is not like they will not occupy these orbitals, the electrons they will not prefer these, or they it is not like that. If it is empty, electron will occupy these orbitals, and the bond formation will take place, right? So here, as you can see, that anti-bonding orbital is not about the bond formation, it is about the overlapping. If the overlapping matches, then it forms the bonding orbital, right? If the overlapping is not matching, see, if I have to tell you about the sigma s, you know that the s orbitals are spherical in nature. So this, suppose this is the positive side and this is the negative side. Again, this is positive and again, this is negative. See, now this overlapping between these two s orbitals, here the positive and negative, destructive and constructive orbitals, in which we are talking about in the MOT sense, if then we are going to tell you about this constructive and destructive bonds. But here, if these plus and minus are interacting with each other, then the resulting orbital will form as an anti-bonding orbital. It is not like that electron will not occupy these orbital. It is like having the higher energy than the bonding orbitals, but these orbitals can also have the electrons with them, right? So if this positive and negative overlapping takes place, then it will give rise to the anti-bonding orbital, because here the energy is mismatched, right? The energy is not matching, so that is why the higher energy orbital is getting generated. But if this positive positive overlap is taking place, if there is another s orbital which is overlapping this positive side and this positive side matching, then this will give rise to a bonding orbital. This bonding orbital will have a lower energy than the anti-bonding orbital, but here electrons are going to fill in both of the orbitals, right? So it is just the concept of the molecular orbital theory, that if a molecular orbital is there and the overlapping is constructive, then we will end up um, having a bonding orbital, right? And if the overlapping is destructive, then we have the anti-bonding orbital. Yeah. So electron will fill in both the cases, but here there is a discrimination, and this is there is a way to calculate the basically the bond order, right? Which will be we will be studying in this next slides only. So here we are going to calculate the bond order, na? then these concepts will come into play, that why we are arranging these things in the bonding orbital and the anti-bonding orbitals, right? So this is how it is. So the electron will occupy all the orbital respective of bonding or anti-bonding. It's just a representation, and these are the overlapping which molecular orbital diagrams show us, right? So I hope it is clear to you now. Okay, welcome. So this is how it is. So now this electronic configuration will play an important role when you are calculating the bond order, bond length. Then you will know which bond is feasible and which bond is not feasible, right? So now I hope this question is clear to all of you. So we are moving forward to question number 8. So here they are saying that draw all the resonance structure for the following. Similar line of question which I have asked previously, the resonance structure. So guys, here there is a carbonyl, there is a amide group and this aromatic ring. So now you have to calculate the resonance structure, number of resonance structure. So can someone tell me how many resonance structure could be possible for this? Just draw it, just visualize it. If anyone can answer, any guesses? It doesn't about right or wrong answer. Any guesses, guys? Okay. Okay, so see how you are going to calculate the resonance structure. So now, sorry, yeah, three or two. How many are three? How many are saying three? Okay, three. Sure or two? Okay, so see what is happening here is, see guys, first of all you can write, see here it is not in the conjugation, right? You are thinking that it is in conjugation with this and then this carbonyl is going up. It is not like that. So because there is no conjugation between this carbonyl and this ring, that is why this resonance structure is not possible here, right? So here only two resonance structures are possible. Either the carbonyl bond get polarized as a positive or negative side. Either this get polarized or this nitrogen lone pair will donate the electron towards this carbon. It is better if I write in this, right? Yeah. It will donate the electron toward this carbon and this carbon will get this. So this is how it is getting generated, this resonance structure. So either this or this. These both structures are possible for this particular configuration. Any doubts in this? I think someone is joining right now. Okay, so you guys are answering in this chat box also. So is it understood or not that how these two resonance structures are there only? Any doubts, guys? Yeah, it is actually homoaromatic. See, homoaromatic is having an sp3 carbon in it, right? So that is why we are calling it as this homoaromatic. This is a sp3 carbon which is present in this ring. That is why it is homoaromatic and it is not participating in this conjugation. So here there are two possible structure that could have either this carbon will get polarized or either this nitrogen lone pair will donate to this bond and this carbonyl oxygen get a minus charge. So these are the two structures that are possible for this particular uh, system. Is it understood? Okay. Any doubts in this question? Okay. So I'm moving forward. So here we come to problem number 9. So here, actually, I have given you the answer now. Okay. So they are asking that which of the following compounds has the smallest bond angle in its molecule. So as you can see, I have not added any animation, so that is why it is clear to all of you, but it's okay. So here they are asking that which compound has the smallest bond angle in its molecule. So as you can see from this picture, this H2 is having the smallest bond angle, but now the concern is why. So can anyone tell me why? How this bond angle is smallest and largest for any compound? Any guesses? Yeah. Yes. So here we are going one by one to all the four, right? So now at oxygen we have two lone pairs of electron, right? So in the H2O case, here the lone pair of electrons are present, and also this oxygen is very electronegative, right? When you compare this H2O with ammonia, here this oxygen having the more electronegativity than nitrogen. Sorry. So here two lone pair of electrons are also present. So here this electrons of this OH bond is more towards the oxygen atom rather than the hydrogen atom. So here the electron density at this particular position, at this position of oxygen, is higher than hydrogen, right? So at this position the electron density is higher because of the electronegativity of oxygen. It attracts the shared pair of electron towards itself, and here in the OH bond the electron will move towards the oxygen more, right? So here the electron density is very high. So now, due to the electron density and the electron crowding which is there in this oxygen case, the bond angle between this OH, this oxygen, hydrogen, and oxygen, this bond angle will get higher. Okay, it will get increased because of the repulsion between this electron density. So that is why the bond angle is getting high. But in the case of H2S, if we go to the H2S, the sulfur is not that much electronegative. So the electronegativity difference between sulfur and hydrogen is very less. So here the electron density is somewhere between this HS bond. So here there is no electron crowding which is occurring at this position, and here there is no electronegativity which is coming into picture. So the electron crowding and electron pushing pull effect is not there basically. So the crowding is not there. That is why the sterically hindered side is not there. So the H2S is having the more smallest bond angle than H2O because of there is no electronegativity, there is no lone pair that is present, so that is why it is quite smooth with the bond angle, so having the lower bond angle. But when you go to the ammonia, now you can claim that nitrogen and oxygen both are the electronegative atoms, right? So yet oxygen is more electronegative than nitrogen, but yes, it is also electronegative, right? So here the electron density is present at this position of the NH bond. Here also crowding is taking place. The steric crowding is there, and here the lone pair is there, right? So due to the steric crowding, the bond angle between this NHH bond, H and H bond, will get increased so that the molecule will get a more relaxed configuration, right? But here the angle is higher than this H2O. Why? Because we are studying that oxygen is more electronegative, so electronic crowding will be higher between this position, so there would be more repulsion between the electrons here. So the angle should be higher than the ammonia, because here nitrogen is not that much electronegative, and so the electron crowding is not in comparison to oxygen. Getting my question? But here you are getting a higher value for bond angle for ammonia than water. Can anyone answer that? Any guesses? Why is it that? Are you guys able to understand my question? What I'm asking? See, what I'm asking here is the oxygen is more electronegative than nitrogen. Fine. And we are studying that the bond angle concept is fairly dependent on the electronegativity and the lone pair bond pair repulsion, right? So here, yet oxygen has a higher electronegativity than nitrogen. The steric rounding at this position is higher than nitrogen, but then also it is having a small bond angle than ammonia. See, what is happening here is because you have two lone pair of electron in the case of oxygen, but in the case of nitrogen there is only one lone pair of electron that is present. So here, if you stretch the bond angle more, then you will feel the repulsion between this lone pair and bond pair more, because there are two bond pairs, so you cannot get as much relaxed configuration than ammonia, because here there is only single lone pair that is present in the molecule. So it has a liberty, or it has an advantage, so to release the strain. So that is why the bond angle is higher in the case of ammonia rather than water. And when we go to the SO2 molecule, you can see that oxygen having the more electronegativity. So here the electron density will be lying here. So it will be having more electron crowding at this oxygen at this end. So that is why they will be try to repel each other as much as they can. So that is why they have the 119-degree bond angle. So now the smallest bond angle is for H2S, because there is no much electronegativity difference between hydrogen and sulfur. Both are like that. So that is why we are getting a smallest bond angle for this molecule. So any queries in this question? Why water is having a lesser bond angle than ammonia or something? Any query, guys? Bond angle. See, these are the experimental equations, right? So basically, you have to do some DFT and some calculation for this. There is particular field for that, where you have where you are calculating the bond angle, the bond distance between the molecules, in which they will be highly relaxed, or highly what should I say? The energy is very low, right? So molecule will try to attain a very lower energy state. Okay, that is why it is releasing all the kind of strains. So in the case of water, here, because of the electron crowding is getting higher, because of the electronegativity of oxygen, it will try to move the two two bonds as far as they can, so that to release the strain which is occurring in the molecule. Sorry. See, it is not that there is a instrument to calculate. These are the calculation. What I'm saying, there is a model or something like that, because computational studies are only based upon these bond angles and the bond length of these molecules. So you have to go for the DFT calculations. So this is the another aspect of chemistry, so you have to go for that if you want to understand more of these bond angles and distances. So guys, you have to understand that DFT calculation. So here I cannot elaborate that these things, because it is experimentally calculated. It is not like you have written that much. It is the generalized things which we are getting from it, that ammonia is having higher because of electronegativity or the non-pair bond pair repulsion. These are the understanding of these languages, right? So we are not here to calculate. We are just crisping the things, so that we can know how these values are correlating with our studies, right? So there are particular calculation that is on a DFT calculation you can do for that. Okay. So if you have interest, you can go through that DFT calculation setup. You can Google, or you can find on the YouTube DFT calculations. You can pursue that things. Am I clear? Any other question rather than that? So here the correct answer is H2S. Fine. This is the smallest bond angle that is present in this molecule, and all other molecules are having lone pairs and electronegative atom. That is why we are getting the molecule will try to release the strain and go in a higher energy, lower energy state. So that is why these calculations are there. So any other doubt in this question, guys? Okay. So I'm going to problem number 10. So as I am saying about the bond order, so here comes the bond order question. So here you have to calculate, find the molecule having the highest bond order. So amongst these, you have to list which is having the highest bond order, right? So for calculating the bond order, here, first of all, you need to know, joining now. Okay. So here you have to calculate the highest bond order. Which of the species having the highest bond order? So first of all, you need to know the valence electron which is present in these species. So for oxygen, we have already calculated that oxygen has how many electrons present in it? 16 electrons, right? So we have previously discussed that there is also a sigma 1s that I am not writing in this configuration, but you have to consider is sigma 1s and sigma 1s star. Star means anti-bonding orbital, right? So here, if you have 16 electrons, here we have 16 electrons. And for this species, we have how many? 15 electrons. And for this species, you have how many electrons? 17. Yeah. And for this species, you have 18 electrons. Fine. So these are the electrons you have. So now you have to assign the electronic configuration of each of the four. So we are going one by one. So here in the case of oxygen, as we have seen earlier, the two electrons are present in sigma 1s. The two electrons are present in sigma 1s star. Another two electrons are present in sigma 2s and 2s star. So here 2, 4, 8, 10, 12, 14, sorry, something I missed, right? Sorry, 2, 4, 6, 8, 10, 12, 14, and 16, right? So here the 16 electrons are getting arranged in this configuration, right? So here bond order corresponds to, basically the basic formula of this bond order is the orbitals number of bonding electrons minus number of antibonding electrons, basically. So you have to calculate the number of bonding electrons and number of antibonding electrons. So quickly tell me how many number of bonding electrons are present in oxygen. Bonding electrons, I am saying. See, here the star, there are 10, right? Here, see, what happens here is, yeah, 10. Because here you are seeing because of the 2s orbital. You are not seeing that 1s is also present. I'm mentioning 1s here. So here we have 10 electron that are present in the bonding orbital. Fine. These are 10 in the number. So how many anti-bonding electron that are present? Anti-bonding, I'm saying. See, anti-bonding corresponds to this. Sigma 1s star is anti-bonding. Yeah, 6 electrons are there. How? Here, sigma 1s star having the 2 electrons, sigma 2s star having another 2 electrons, sigma 2p star having another 2 electrons. So 2, 2, 2 is equal to 6. So this is how we are having number of anti-bonding electrons as 6. So total, if we minus this, we will have 4. So after dividing it by 2, we'll end up having 2, right? So this is how we are getting this 2. So the oxygen bond order is 2. And also we will write it as this, right? There is a double bond between oxygen, fine. So oxygen bond order is corresponding to 2. So now if we go to O2 plus, sorry. So we are basically taking out one electron from this oxygen molecule. So if we take out one electron, so here pi 2p star, this is the anti-bonding. So here we are abstracting one electron from the anti-bonding orbital because it is the highest occupied molecular orbital. So from here only, one electron will go. So here, if we abstract one electron in this case, O2 plus, 15 electrons are there. So now, how many bonding electrons are there? Again, applying this formula, bonding electrons are 10, and the non-bonding electrons are 5. Very good. So 10 minus 5, we will corresponds to a number 5. So 5 divided by 2, we will get a 2.5. Fine. So this is the bond order for this particular O2 plus species. So here, and if we go to this O2 minus, so here we have 17 electrons. So basically we are adding one more electron into the oxygen system. So oxygen already having a 16 electron species, adding one electron correspond to 17. And now if we have to add another electron in the oxygen system, where it will be adding pi star orbital as we have seen earlier, right? Only the pi star orbital is the orbital in which the oxygen another electron is getting added up. So this is the configuration now. So the electron is adding in the anti-bonding orbital. So now how many electrons are there in the bonding orbital for this O2 minus? Again, the number of electrons will remain same for the bonding orbital because there is no electron adding in the bonding orbital or abstracting from the bonding orbital, right? So the bonding orbital electron will remain same. But here the addition is occurring in the pi star orbital, that is an anti-bonding orbital. So now here we will be in the case of oxygen, we are having 6 electron in the bonding orbital, right? Sorry, anti-bonding orbital. So now in the case of O2 minus, we will be having how many electrons in the anti-bonding orbital? 7, right? Yeah. So 10 minus 7 corresponds to 3. When you divide this 3 by 2, you will get a value that is 1.5. So the bond order for O2 minus will be 1.5. So now if we go to O2 2 minus, that means 2 extra electrons are getting added in the oxygen system. So now the 2 electrons will add up in these pi star orbitals only, right? Because first of all, according to the Hund's rule, we have to first place, uh, we have to occupy a single electron in all the species, the degenerate orbital. We have to occupy one electron in both the shells, and then we will doubly occupied it, right? So here, if 2 electrons are getting added, one will get added here, and another will get added here. Fine. So this is how they are getting added in these O2 2 minus. So now if we have 10 bonding orbitals in this case, we are also having 10 bonding electrons in this case, right? So this bonding orbital number is not getting changed. What is changing here is the pi star 2p orbital are having two extra electron in this. So the number of electron in the non-bonding orbital is getting increasing now. So what is the number now? In the anti-bonding orbital of O2 2 minus, how many electrons? Sorry, 8. Yeah. So 8 electron will be there. So 10 minus 8 will leads to you a 2. So 2 divided by 2 will get you 1. So this is how molecular orbital theory will tells you about the bond order. So how you are going to calculate it is solely based upon the molecular orbital theory. So this is how you are going to get the molecular orbital and the electronic configuration, out of which how you are going to calculate the bond order, it is depicted like that. Okay, so here comes the application for this molecular orbital theory. Okay, so now the question is molecule having the highest bond order. So which will be the molecule having the highest bond order? O2? Yeah, plus will be having a highest bond order. So any query in this question, guys? Any query in assigning the electronic configuration and assigning the bond order? Any questions? Okay. So I'm moving forward to problem. Yes, yes, yes. Bond order. See, actually, I was thinking to elaborate in the next slide, but still, if you are asking, see what happens in the case when you have to understand the bond order. It is actually dependent on the bond strength. Basically, how an atom is connected to other atom, how the bond strength is related, it is going to depicted by the bond order. So if oxygen has a bond order 2, that means that it is having a strong bond rather than this O2 plus, O2 minus and O2 2 minus. So the weakest bond between these four species will be O2 2 minus, because bond order is directly proportional to the bond strength. Basically, it is giving you an idea that how much bond energy you will, basically bond dissociation energy you need to dissociate that bond, right? If you understand from that concept of the bond dissociation energy, so here, if bond order of O2 2 minus is 1, which means that all of these species, the bond order is very low for this O2 2 minus. Okay, so basically, the bond strength between this O2 species, that is a peroxide ion, basically here O2 2 minus, is very low. The bond strength is very low. So you need a low energy to dissociate this particular bond. So the bond dissociation energy among these four will be uh, lower for this O2 2 minus, least actually, least for this O2 2 minus. So bond order will tell you about the bond strength values. So it is related to bond strength only. So how many energy you need to dissociate any bond, or how many, basically you will get an idea, get a picture that yes, the bond is how much strong or how much weak. So this is why we are calculating the bond order. Is it clear? Okay. Okay, so any other questions? If not, I'm proceeding to question number 11. So, in the question number 11, they are asking the oxygen molecule is paramagnetic. It can be explained by which of the following? Resonance, hybridization, valence bond theory, or the molecular orbital theory. So, guys, oxygen molecule is paramagnetic. How do you know that? By resonance, can anyone tell paramagnetism and diamagnetism? Yeah, molecular orbital theory, the correct answer is that. But here, oxygen as paramagnetic cannot be justified by resonance. Hybridization is not going to tell you about the paramagnetism. Hybridization is just tell you the structure of the basically the how it is arranged. And also valence bond theory will dictates you the structure, the geometry of the molecule, right? So here only the molecular orbital theory will assign the particular electronic configuration for the molecule and will tell you that how many electrons are uh, not occupied, right? So here, if we see in the case of oxygen, we have studied this molecular orbital diagram that yes, here the two electrons are partially filled, right? These orbitals are partially filled, so orbitals are partially filled. Because of this, the two electrons are free. So here it is paramagnetic. It is justified by molecular orbital theory rather than resonance, hybridization, or any other valence bond theory. So these three things are not going to tell you about the paramagnetism, diamagnetism. It is a molecular orbital theory which will be able to tell you the paramagnetism, diamagnetism in a molecule. Okay, is it clear to all of you why molecular orbital theory is dictating the paramagnetism? Okay. So moving towards the problem number 12. So here they are asking which of the following electronic configuration will obey the Hund's rule. So as I am continuously focusing about the Hund's rule, so what is Hund's rule? You have to first know that. It is a very basic question, guys. I'm just adding these questions in these slides because this is a first tutorial. So the basic concepts should be clear at this point only. So that is why I am including these slides. So here, first of all, you need to know what is Hund's rule and how this electronic configuration is affected by that Hund's rules, right? So Hund's rule is states that the electrons having same spin enters the orbital of the same energy one by one, which I am repeatedly telling you that yes, first of all you have to, if there are orbitals having same energy, the degenerate orbital. In this case, you can see 2p has three degenerate orbitals, right? So you have to fill the electron in such a way that first of all you have to fill a singly to all the orbitals. Single electron should be there in this x, y, and z orbital of this 2p. Fine. And then you have to couple it. Then you can fill the another electron. Then the pairing of electron can be done, right? Otherwise, you cannot fill directly the two electron in this system and leave these orbitals blank. So this is what Hund's rule states. So according to the Hund's rule, pairing of electron does not take place until all the orbital of the same energy are singly filled. So singly occupied and then the doubly occupied region can take place, right? This is what Hund's rule state. So now the particular question which comes into picture is which of the following electronic configuration is obeying the Hund's rule? So is it option one? Yeah, option one, right. See, this is the correct answer as we know, but here why it is a correct answer? Because p orbital are all first singly occupied and then another electron is adding to this px. Fine. Why this 2 is incorrect? Because here x and y, the two orbitals are singly occupied and then doubly occupied, but here z is not occupied at all. So first of all, one electron is should be there in this px, py, and pz, and then the pairing of electrons are done. Here, in this case as well, these three orbitals are degenerate, but uh, one orbital is empty, and instead the pairing of electron is done in this orbit. Fine. And here also this py is 3, whereas it should be 2px2, 2py2, and 2pz2. So here pairing of electron should be there, and also the maximum limit is also for the p orbital, py orbital is 2, and here the electrons are feeling like 3. So that is why it is the wrong answer. So the correct answer is 1. So first configuration is obeying the Hund's rule. So is it clear to all of you? Okay. So it is a very basic question, guys. So it's just because to revise your Hund's rule, Log principle, Pauli exclusion principle, you have to know that. So it's just revising the things. So coming to the question number 13. So now they're asking how many unpaired electrons are present in N2 plus. Unpaired electrons, right? So N2 plus. So First of all, what you have to do to calculate this unpaired electron? Write the elect yeah, electronic configuration. First of all, you need to write the electronic configuration. So in the case of nitrogen, what is the total number of electrons that are present? It is not N2, right? It is N2 plus. So there are only 7 electrons that are present, right? There are 7 electrons that are present. But if you are saying that this molecule is N2 plus, this plus, fine. If you are saying like that, you can understand by both the ways. So how many unpaired electron in this N2 plus will be having? So here, if you get to fill this 14 electrons, how many electrons are there? 14, right? So in amongst the 14 electron, one electron is abstracted. So now how many electrons are remaining? 13 electrons, right? So here sigma 1s is getting filled. First of all, 1s, 1s star, 2s, 2s star, px, py, pz, and then the anti-bonding orbitals will fill. So here 13 electrons are there. So V corresponds 2 electron in sigma 1s, 2 electrons in sigma star, sigma 2s, and 2 sigma star, that is 4. So total number of electron up to here is 8. So 9, 10, 11, 12, and 13. So 13 electrons are there, right? So here, how many how many unpaired electron is present in the system? In the case of N2 plus now. Yeah. Because here you are constructing the molecular orbital diagram, right? So you need two atoms. Yeah, one unpaired electron is there. Because now you have 13 electrons. If I will say that how many unpaired electrons is present in N2, nitrogen. Can anyone answer how many unpaired electron is present in N2? Yeah, 0. Because here 14 electrons are there, if then this orbital is also now paired up. So that is why now the single electron is getting paired up. So here in the case of N2, there is 0 unpaired electron that is present. But in the case of N2 plus, as you are abstracting one electron from this system, so this is why here this particular electron is not there now. So one electron is singly occupied. So here we are saying that one unpaired electron is present in the system of N2 plus, and N2 having the uh, 0 unpaired electron, right? And in the case of N2 minus, how many unpaired electron? Yeah, one. Again one. Because in the case of N2 minus, you have 15 electrons. So for 15 electron to be filled, you have to fill this. You have to fill this. So here also you are having one unpaired electron. So is it clear to everyone how many unpaired electrons are there in the system? The correct answer will be option number D. Yeah. So any queries in this question? Any difficulty to understand? Any questions, guys? Okay, so no questions are there. Okay. So if no questions are there, I'm moving forward. So coming to the problem 30. Sorry, 14. What is the bond order for nitrogen? See, I am just giving you a gist for this bond order and the molecular orbital diagram. So that is why I'm incorporating these nitrogens, oxygen, and not the very complex systems. That is why I'm just incorporating that thing so that you can grasp the thing as earlier than it could be possible, right? So here they are asking what is the bond order of nitrogen. So if you have to calculate the bond order for nitrogen, what you have to see is the electronic configuration you have to write for nitrogen according to the molecular orbital. So here if you go to write the electronic configuration for nitrogen, as nitrogen is having how many electrons, as we discussed now, 14 electrons, right? So if you write the electronic configuration for N2, the 14 electron configuration will be like this. The sigma 1s orbital having 2 electrons, star orbital will have again 2 orbitals, 2 electrons. So here the electronic configuration is like this. So now they are asking what is the bond order. So guys, you have seen this basic formula for bond order, how we are going to calculate it. So here the number of bonding or by electron that are present in this electronic configuration is how many number of bonding electrons are present in the N2 configuration. How many number of electrons are present in the bonding orbital of nitrogen? Can anyone answer? 10. No, I'm not saying the electronic configuration or the total number of electrons. I'm saying about the bonding orbitals only, right? So the bonding electrons are 10. Yeah, 10. So here we have to minus the anti-bonding electrons. So now the anti-bonding electron will be 2, 4, only 4 are there, right? Yeah. So you have 4. So 10 minus 4 will be 6. So now you have to divide it by 2. So what is the bond order? What is the value? 3. So now the bond order for N2 molecule will be 3. So the correct answer will be, what's the bond order of nitrogen? It would be option number A, that is 3. Fine. Any doubts regarding this question? Any doubts, guys? Okay. So if there is no doubt, I'm moving forward. This is actually the molecular orbital diagram for N2. So you can see here how these arrangements are done. So please practice this electronic configuration, writing the electronic configuration for all the molecules so that you will get how the MOT diagram is getting constructed. So this is how it is, right? So coming to the problem number 15. So they are asking, what do you think the relationship between bond order and bond length? So, what would be the relationship between the bond order and the bond length? So, the options are directly proportional, indirectly proportional, no relation, and cannot predict. So, here we have seen then bond order will tells you about the bond strength. And now we are also figuring out about the bond length. So, what will be the relation between these two aspects, guys? One is saying that how much strength does your bond have, it is dictating that, and the bond length is the another aspect, because as long as your bond length is high, then your strength of that bond is weak. Agreed or not? If I tell you that you have two molecules, see, if I tell you that this is Hi and this is Hf, who is having the higher bond length? Who is having the higher bond length? Hi or Hf? Which? I'm not get you. FH. Having the higher bond length. Why? IH. Okay. See, what you are thinking is about the electronegativity aspect, right? But here are two aspects which come into play. You have to know both of them. See, here HF is electronegative, then iodine, uh, and will obviously attract the shared pair of electron towards itself, due to which you think that this uh, bond length is getting longer, right? But here there is another aspect, that is the atomic radius. So for iodine molecule, the atomic radius is very high. Iodine is way bigger than fluorine molecule. So that is why this iodine and hydrogen, the bond length is high because of the atomic radius of iodine. Whereas the fluorine is a very small molecule, and here the ionic radius for this fluorine is very low than iodine. That is why this HF bond is not having that much bond length than HI molecule. So HI having the very high atomic radius, that is why this HI molecule having the higher bond length than HF molecule. If I say that who is more polar, so what will you say? Which is more polar in amongst these two? HF is more polar. Yeah. So HF is more polar. So this is what about bond length, and this is what about bond strength. So here the strength of this HF bond is higher than HI bond. So now just tell me what could be the possible relationship between this bond order and bond length. You can also state according to this. See, yeah, inversely proportional. How? See, according to this, why people are just joining right now, I don't understand. I mean, okay, okay, guys, coming back to your question. Sorry for the disturbance. Okay, so here we are talking about the bond order and the bond length. So here you can see that the bond order for C triple bond C is 3. The strength of this L, basically alkyne bond, is higher than alkene, which in turn is higher than alkene bond, right? So here bond order for C triple bond C is 3, single bond is 1, and the double bond is 2. Whereas if you talk about the bond length of this particular triple bond length, okay, I'm saying about the bond length. So the bond length of this C triple bond C, is it higher or lower than C double bond C? Can anyone tell me? The bond length for C triple bond C is higher or lower than C double bond C? Lower. See, the C triple bond C bond bond length is lower than C double bond C bond length, because here the carbon having the uh, three bonds. So here two pi bonds are present in this alkyne, and one sigma bond is there. Whereas in this case, one pi and one sigma bond is present in the case of C double bond C. And in the case of C single bond C, only a sigma bond is there, right? So the bond strength for this C triple bond C is very high, but the bond length is very low. So the inverse proportional relationship is coming according to this picture. So if you understand this simple alkene and alkane relationship in the bond order and the bond's length, then you will easily compute the relationship between bond order and the bond length. So now if we consider that bond order for alkyne is 3, that the bond order is very much high for alkyne, but the bond length is very low, because now the strength of this bond is very high. So the two atoms are very much closer to each other than in the case of double bond, right? So here we can compute that these two aspects are inversely proportional to one another. So these are inversely proportional. So bond order will be inversely proportional to bond length. If the bond order will increase, the bond length will automatically get decreased, because as you can see, in the case of C triple bond C, the bond order, the bond strength is high, but the bond length is very low because it is highly compact. This is highly like rigid system, that it is interacting highly with each other. So that is why the length of these two bonds are these between these two atoms are lower. Is it clear to all of you how this inversely proportional relation is there in between bond order and bond length? Any questions regarding this? Any confusion? Why they are indirectly proportional? Okay. No question. Everyone understood the concept? Okay. So if so, this is the last question actually. This was the last question for today's meet. So I'm ending this session here. So, guys, I hope you got all your answer for this particular question. So, these 15 questions are the very basic questions from the point of the introductory organic chemistry course which we are starting. So, here we are discussing about the little bit concepts which will build up your further concepts, right? So, this is the starting point from which we are building up, and so that we can build up the other 7 weeks classes. So, okay, so now we will be meeting on the Saturday, 6 to 8. So please be there in the next class. And if you have any doubt regarding these questions, please feel free to ask me in the next session. Or this video will be available on the YouTube. You can go through once again, or how many times you want. So you can comment on that particular video so that I can get your question, or you can ask in the next lecture. So I will be available both the ways. So anyway you will find free, anyway you will find comfortable, please feel free to answer question, right? So thank you so much for joining this session and being so interactive. So thank you so much, guys. So I'm ending up this session right now. Okay, so thank you.